All right. I'm sorry that I'm not here with you in the morning, but this is what we're going to be doing. We're going to be taking notes. So let's go ahead and see if we can do this. These are your notes. We are going to be taking notes on air. Before we do that, though, we've got a daily question. Your daily question is on the board, and it says, what do you think air pressure is? So I want us to think about what we think air pressure is. And I've got a little picture here for you. I'm showing this is sea level. This is the level of the sea. And so we've got a higher air pressure here, and we have a lower air pressure up here on the top of the mountain. So we're going to be talking about what we think air pressure is. All right, I'm going to move this over here so that I can move my board. And I've got this. Hopefully we can get this going. Ah, love it. So that we can see what it is we're doing. So when we're talking about air pressure, air is something. Air is stuff, okay? If you do this, right, you can feel the air. So air is a mass, or rather it's a substance. So what do you think air pressure is? What do you think air pressure is? And if you need to go ahead and pause the video right now to give yourself about a minute's time to think about it and write something down, you can do that. Okay, so air is a substance. Air is matter. And if air is matter, air has mass. Let's see, I think I'm going to make my pen a little bit smaller today. So air is matter. It has mass. Okay, if air is matter and it has mass, each one of those little particles of air, those molecules of air, can push. If it has mass, it can push on you. It has mass. If it has mass, it can apply a push force. So air is matter, it has mass. If it has mass, it can apply a push force. It can push on you. And so we feel that push when we go outside on a windy day. Air might be invisible, gas might be invisible, but we can still feel the effects of that gas, which is kind of cool when you think about it. Okay, so then air pressure is this push of air on us. And if we are looking at sea level, we're going to have a higher air pressure because there is more air pressing down on top of us. All of this is a column of air, and it is pushing down. If you are up on the top of a mountain, you are going to have less air pushing down on you here. If you're at the bottom of the mountain, you are going to have more air pushing down on top of you, quite simply because there's more air molecules that have been pushing down on you. There are less air molecules pushing on you there. So that's air pressure. Air is matter, so it has mass. If it has mass, it can apply a push force on you. And so that is what you are feeling. Okay, so that's that. Today what we're going to be doing is we are going to be looking at air notes. And I'm so sorry, I am not going to go ahead and help you set up your table of contents, but I'm sure that you can set up your table of contents as far as what the date is and where to put these notes in your table of contents. And then please remember to also write down your page number. Okay. So I want you to open up, please, to your notes. If you could. They are atmosphere air notes, and I've tried to separate this so that we can see everything on one screen. I don't know if I'm liking it or not, but we're gonna just kind of make it work as best as possible. So I'm gonna drag this down just a little bit, and I'm gonna do my very best to go ahead and read this for you where it says air notes. So it says, the atmosphere is a cloud of gas and suspended particles extending from the Earth's surface out many thousands of miles. We talked about what the atmosphere was when we looked at our four spheres. It becomes increasingly thinner and thinner with distance. So the atmosphere thins out, which means the air thins out. So the farther away you go from the surface of the Earth, the less air pressure there is. But it's always held in place, this atmosphere, this air, with the Earth's gravitational pull. The atmosphere surrounds the Earth and holds the air that we breathe. It protects us from outer space and holds moisture in the form of clouds. Remember, those are liquid water, gases, and then tiny particles. It is the protective bubble in which we live. And so we can divide the atmosphere into 5 regions or layers. So what I'm going to do, whoops, Miss McRae, sorry, I was on the wrong side. So we're going to divide the atmosphere into 5 regions or layers. I'm going to come over here and do that. This is going to be great. So scientists use variation in temperature to divide the atmosphere into 4 vertical layers. I'm adding a 5th. So we have got the troposphere, we've got the stratosphere, we've got the mesosphere, we've got the thermosphere, and we've got the exosphere. Exo is the layer right before we exit. So we need to go ahead and write those in right here. Troposphere, that's where we live, us. Okay, we live here. We've got the stratosphere, so this is where we live. Then we have the stratosphere. We have the mesosphere. Fourth layer is the thermosphere. And then the last layer before we get into outer space is the exosphere. After this, we exit out. We leave our Earth's atmosphere and we are on our way to outer space. Right. This is going to be tricky. We got this. Okay, so the atmosphere is a mixture, okay? It's a mixture just like anything else. If you put a bunch of beads in a bucket and mix them all together, that's what we have here. So the atmosphere is a mixture of nitrogen, 78%, and 21% oxygen. And then we also have water vapor and many other gases. So we're going to say it's a mixture of 78% nitrogen, and 21% oxygen. And then there's a whole bunch of other layers. And you know what? I'm going to show you air. How can you show us air, Miss LaGrange? This is air in a bottle. And so what this is this is the combination, or rather composition of air. So if we were able to go ahead and look at air, this is what we're seeing. And I bet you can guess what the yellow beads are, because the yellow beads are most of what we see is most yellow. That is the nitrogen. It is 78% nitrogen. And then if we are looking at the red particles, then the red particles are going to be, what's the oxygen? Okay, so that's what we've got in here. And if you look, a lot of people think most of it is all oxygen, but most of it is actually nitrogen. And since we talked about parts per million yesterday, there are 780,000 parts per million of nitrogen molecules, in nitrogen atoms in the air that we breathe. So that's the air. Okay, awesome. And then you have a different mixture, you have water vapor, and then different mixtures of different greenhouse gases. And we'll talk about greenhouse gases when we start talking about climate. Okay, so you, along with many other things, we live in the troposphere. And that's what we said here, us. We live here in the troposphere. So let's go ahead and look at properties of air. Okay, so it is made up of matter, and so because it's made up of matter, it has mass. We talked about that in our capture question. Made up of matter, which means it has mass. I think I'm going to turn this into black so that we can see it just a little bit better. That might be too thick, but we'll see. Okay, so it's made of matter, it has mass. Oops. It takes up space, so has volume, which can change. So it takes up space, and if something takes up space like you do, it means it has volume. Okay, it takes up volume, and that can change. You can change the volume of air. And you might be thinking, how in the world can you change the volume of air? And I think we talked about that a little bit. You can heat it or you can cool it in order to change the volume of air. So let's go ahead and look at the properties of volume. All right, so it takes up space, we can change it. It expands when heated. Expands when heated, which means that it is less dense. And if it's less dense, it rises up. Then it can contract when cooled. And if it contracts, it means that it is more dense. And then it sinks back down. So I know that I talk about interpretive dance a lot, but it's true. If you heat it up, it expands way out, and then if you cool it off, it contracts and gets small. And I want to show that in a demonstration right now. I'm going to attempt to crush this can, with nothing but air. So here's what I'm doing. I have heated the air in the can. So now the air in the can is really expanding out and pushing on all the sides of the can. Now what I'm going to do is very quickly cool the can off. And you can see that when I cool the can off, the air in the can got really small. And so since the air in the can got really small, there was no more air pushing on the sides of the can on the inside. This was an open can of soda. And so what happened is the outside air, because there was no inside air pushing on the can, the outside air started pushing on the can on all sides, and it crushed the can due to air pressure. Okay, so that's what happens. We can crush things. Air pressure is very, very powerful. And this can's not crushing, it's open, because the air on the inside is balanced with the air on the outside. Air on the inside's pushing out, air on the inside's pushing out, air on the outside's pushing in, and they're in perfect balance. Once I made the air inside really small by putting it in cold water, the air inside contracted, the outside air came in and was pushing the insides of the can. Okay, so I'm going to move that over here, get that out of the way, so we can look at another demo. Fabulous. Don't break. All right, so let's go ahead and look at some more behaviors of air. It can exert pressure or force because it has mass, and we saw that with our can. So I'm going to move this down a little bit so we've got some more space. So, can exert pressure or force? Can exert pressure. Which is force, because it has mass. We saw that, squish the can. Something else we need to know, so behaviors are what air does. Air moves if there's a difference in pressure. Air can move. Air can move. How does it move? Because of pressure differences. It can move because of differences in air pressure. Okay, when air moves, air is always going to move from areas of high to low. So there's a little kind of like, I don't know if anybody's ever seen Snow White, but it's like high, low, it's off to the pressure I go. Ba-dum-bum-bum, ba-dum-bum-bum, high, low. The air will move from high to low. Moves from high pressure to low pressure. Oops. High pressure to low pressure, and we call this wind. When air moves from areas of high pressure to low pressure, this is wind. All right, so we're going to do another little demonstration. Oh, this just says, this is like if you put a small child in a plastic bag, which you shouldn't do, but like a garbage bag, don't put their head in, and then you suck out all of the air with a vacuum, the outside air is going to push in so much that that child's not going to be able to move their arms at all. So that's just something that we used to do. We're not going to be doing that. All right, so we're going to do a paper bridge pair share. So we're going to go ahead and set this up, and I want you to think about what might possibly happen. I have got, let me move my air out of the way. I have got a bridge that I have created out of paper and books. And what I'm going to do is I'm going to blow air underneath this bridge, and I want you to imagine, what do you think is going to happen to the paper? How will the paper react if I blow air underneath the paper? Okay, so we're just going to pause for a minute and give you time to think about that. So let's go ahead and try it out. Try one more time. One more time. Okay, when I was blowing underneath the bridge with my air, the bridge went down. Let's see if we can figure out why that happened. The paper did go down. You've got some space right here to go ahead and write that down. Paper equals down. The paper went down. So why do we think that is? By displacing the air molecules under the paper, I went ahead and moved the air molecules out of the way underneath the paper. Here were lots of air. Air, air, air. The air is equalized. The pressure is equalized. I moved the air underneath here, creating an area of low pressure on the bottom. That means the high pressure air, there was more air particles, higher air pressure on the top, pushed down into that space, that empty space, or that lower pressure of air down below. So by displacing the air molecules under the paper, we moved air molecules under the paper. This equals low pressure. Less air is low pressure. So then the more air or high pressure the high pressure on the top of the paper pushed down into the empty space. And it's not totally empty, but into the lower air pressure space. And I want to show you that in another demo. That is why this can happen. And so this is just areas of high pressure and low pressure. What I have is I have a balloon and I've got a fan. And so I'm creating an area or a column of low pressure. So right here, by displacing the air with my fan, this is a low pressure column right through here. And the balloon is staying in it. Now the balloon is staying in that area of low pressure because outside of that column is high pressure. There's high pressure air, more air particles, high pressure pushing and keeping that balloon nice and neat in this column of air. So I can push the balloon a little bit and the higher air pressure just kind of keeps moving it back into place. That's areas of high pressure and low pressure. Okay. So this brings us to weather. All of this areas of high pressure and low pressure is where we can start thinking about how weather ties in. And this is weather is what we experience in our troposphere, where we live. So differences in air pressure drive our weather system. Differences in air pressure drive weather systems. Okay, so then what causes these differences in air pressure in our troposphere? It's because we have areas on our planet that are being unequally heated on the Earth's surface. And we talked about what the main energy source was for our Earth, and that's the sun. So if we look at what's going on with our globe, it's not flat, it's round, it's spherical shape. And when the sun's rays come in, the most direct rays are here, and then we have indirect sunlight up at the poles because it's a round shape. And so we get more heat here, less heat there. So this unequal heating of the Earth's surface starts driving these air currents that move air, move our weather patterns around the globe. So unequal heating of Earth's surface. Okay, so this causes air movement. We call this wind. In the troposphere. Oops, that's not how you spell troposphere. So air movement or wind in the troposphere is caused by the unequal heating of the Earth's surface, as we can see in these pictures. They create those wind currents that we see up here in the graphic. Okay, we're going to go ahead and kind of fill in some things. So heated air rises. I'm going to move this over. You should be on the back side now of your paper. So we're going to look at how air moves. So heated air rises. Okay, heated air will rise up. It expands when it rises, or when it doesn't expand when it rises. When it rises, this is why it rises, because when we heat it, it expands and it becomes less dense. this means there's areas of low pressure on our planet. So heated air rises. Why does it rise? I'm going to show a picture here. Because when we heat it, it expands, becomes less dense, and it creates low pressure. Rises, it expands, becomes less dense, and this equals lower pressure. So if I go ahead and give myself a little dotted line here, I have lots of air particles, and those air particles are spreading out, rising up, moving around. Okay, on the flip side, cool air is the opposite. So looking over here, we see that cool air sinks. Why does it sink? Because when you cool it, it contracts. Think about what happened in our soda can. It means that the air becomes more dense, and so there's more pressure when it is sinking. This is what creates air pressure. So cool air sinks. Why does it do that? Because when you cool it, it contracts. This makes it more dense. This gives it more air pressure. More pressure. And I'll go ahead and do my same little demo here, a little line, and I'm going to put all of my particles underneath the line now, not spread out, because it is cooled, and so the column of air is sinking. Okay. This is why air moves. This is why a hot air balloon also works. You heat the air inside with your burners, with your propane tanks, and then it makes the air inside less dense. The air inside is rising. And there's literally less air molecules in here and more air molecules outside of the balloon. And so this becomes less dense and it rises up through the air. Oh, I have no idea why that's happening. I don't want to learn more. I want to come back here. All right, so a little pair share. We're not going to really do this. I'm going to kind of talk you through it. If you have a hot sidewalk and cool grass, because gosh, you know what? I really want to walk on a nice warm sidewalk and nice cool grass. I can feel summer coming. Describe the air movement and why. So I want us to picture that. You're walking on this sidewalk, it's nice and warm, and the grass is cool beside it. Where is the air gonna move to? I want you to think about that for a second. All right, so here's how the air is gonna move in that situation. The hot sidewalk is hot, so the air above it is expanding out, it's expanding and rising up, creating a low pressure system. So that air is rising. The cool grass, the air above the cool grass is contracting, it's making it more dense, and so it's sinking. This creates higher pressure. So I always said air moves from high, low, it's off to the pressure we go. Ba-da-dum-bum-bum, ba-da-dum-bum-bum, high, low, the air will go from high to low. And so what it's going to do is going to move from the grass, which is high pressure, to the sidewalk, which is low pressure. And you get kind of like this circular system that's happening. Grass is moving in from the cool area to fill that void, that empty space that is being created when the air is rising up, creating a low pressure system. Remember, air always moves from high pressure to low pressure. All right, so how does warm air rise? There are going to be 4 different ways we're going to talk about how air in our atmosphere rises. The first one is called convective uplift. This is convection. This is warm air rises. So I'm going to move this up a little bit so that I'm not blocking when I'm writing. Okay, for convective uplift, Warm air from the ground rises, it expands and cools, because the farther away from the ground you go, the cooler it gets. So it rises up and begins cooling as it's away from the ground. It becomes, contracts, becomes more dense, and sinks back down again, and it continues on this process. So warm air rises. From the ground. It cools and then sinks back to the ground, where it rises again because it warms. It expands and rises up again. And so you get this constant like this, high pressure, low pressure, high pressure, low pressure. So that's one way that air can rise. Another way is something called orographic uplift. Orogeny is the study of mountains. And so when we're talking about orographic uplift, that means the air on our planet has met a mountain, and it can't go through the mountain, and it can't go around the mountain, so it has to go up the mountain. So when wind meets a mountain range like this, the mountain forces the air up, which cools the air. So when wind meets a mountain, it forces the air up, and the air cools. Why does the air cool? Because the farther away from the surface of the planet you go, the cooler the air is. Really warm down by the surface, and then farther up it gets cooler and cooler. And so it cools it. And we're going to learn that when that happens, you form clouds. You go up, and clouds are going to start to form. All right, we're going to talk about convergence. Just like when we talked about plate tectonics converging, this is how air can also be forced up through convergence. When winds are blowing from different directions like this, they meet, they can't go through each other, they can't go around each other, so they force each other up. That's called convergence. Convergent uplift. Winds blowing from different directions. Meet head on and lift up. They can't go around each other, they go straight up. Now we're going to talk about a different thing. This is frontal wedging. Just like it sounds like. When we have a weather front, you have a mass of air and another mass of air, and one mass of air is going to wedge itself under the other, forcing that other kind of air up. So we're going to look at that. Okay, so this is a narrow zone, is a front. A narrow zone between two air masses that differ, that are different in temperature and humidity, meaning how much moisture that they have. Okay, so air holds water and air can change in temperature. So we've got this right here. We've got a cold air mass coming into a warm air mass. Cold air more dense, wedge itself underneath the warm air, forcing the warm air up, and then you can get really bad thunderstorms this way. This is some of the stuff we see in Iowa. If you've got warm air coming into cold air, you're going to have a more gentle rise and uplift of that warm air, and this is going to be one of those kind of like crappy sort of like rainy days drizzling, but you're not going to have big thunderstorms that are scary. That's this case up here, not this case down there. So for frontal wedging, you have a narrow zone. Okay, that's where they meet. That's the front. Between two air masses. That differ, that are different. Differ in temperature and humidity. Humidity is the amount of water in the air. Okay, the more dense air mass wedges itself beneath the other. So cold air always goes under warm. More dense air mass goes under less dense air. And this forces the air up. When warm air goes up, it cools, and all of the moisture that's in there falls out. Because remember when we said condensation and evaporation? In order for water to condensate, to come out of the air, you have to cool it. And so you push that warm air up, and it cools it off quickly, and then all of the water that was in gas form comes out and starts forming clouds. If it happens very, very quickly, you can get severe storms. All right. So those are the pictures: convection, orographic uplift, convergence uplift, and then frontal wedging. Notice this big cloud here. That's a thundercloud. Scary, scary. And it's almost springtime. We're going to start seeing a lot more of those. So let's go ahead and talk about wind. Wind is the horizontal movement of air caused by differences in air pressure. That's how you spell horizontal. Horizontal movement of air caused by a difference in air pressure. So around North Liberty, it seems like we have the worst winds ever. And apparently because we have larger differences in air pressure. So larger differences in air pressure equals stronger winds. Something else that we have in North Liberty is we have a great deal of what's called fetch. And I don't mean like fetch boy, fetch, chase the ball. I mean fetch is the distance wind can travel without being blocked by anything. In Iowa, we don't have any mountains to slow the wind down. And so the wind can travel for long distances. Okay. So when we are looking at these areas of high pressure and low pressure, wind always, or air always goes from high to low, and you can see here that there's a spinning kind of motion. And so high pressure always goes clockwise, and low pressure always goes counterclockwise. And so it moves like this, clockwise into counterclockwise. That's how pressure systems move. All right, large air masses produce high and low pressure systems everywhere on our planet. Large air masses produce high and low pressure systems, I'm going to say on Earth. Awesome. This is a weather map. If you ever have seen the nightly news or you've seen a newspaper with a weather map on it, you can see that we've got areas of high pressure and low pressure. And these lines are what's called fronts. The little flags point the direction, and the color is the temperature. So in this case, we've got cold air, and the air is moving in this direction down here. We've got some warm air moving in this direction, and that makes sense because this is the Gulf of Mexico. Sometimes you can see areas where the warm air and the cold air are coming together. These are all different fronts, that's thin zone where we've got big air masses that are meeting. And it creates areas of high pressure and low pressure. And we can tell what kind of weather is going to be there. High pressure is going to be fair weather. It's going to be nice, not always necessarily warm, but not cloudy. Areas of low pressure are going to be areas where we're going to have clouds. All right, air masses can be classified by two things. We can look at an air mass and be able to tell what kind of an air mass it is by the temperature of the air mass and the amount of humidity or moisture content of that air mass. Humidity is how much water is in the air, H2O. Is it dry air or is it wet air? So we're going to name it. It's either going to be continental, because when air travels over land, it can't absorb any moisture, and so it's dry. This is continental air. It's dry, forms over land or travels over land. Maritime is wet air. This is air that has formed or traveled over water, and so it's got a high level of humidity. It's moist air. Oh. We can also say that the air can be polar, meaning cold. This formed in high latitudes by the poles, away from the equator. We can say that it's tropical air, meaning that it's warm. It formed in low latitudes, meaning by the equator, the warmest area of the planet. So let's go ahead and label these. Air mass can be continental, which is dry, formed over land. I'm going to move this up a little bit so that we can see it better. It can be maritime, which means that it is wet. It formed over water. It can be polar, which means it is cold. Formed in high latitudes. High latitudes would be areas by the poles. Or we can say that it's tropical, which means that it is warm. It formed in lower latitudes. Oops, sorry, this should be high latitudes. Up here, and this is low latitudes by the equator. I'm hoping you're going to have a lot more space to do your writing. I've got everything kind of cramped in really close for us. Okay, so just like I want you to know that when we're talking about air masses, it's what's called a binomial system. Bi meaning two, like bicycle has two wheels. So this is a two-part naming system. So if you are going to be looking at this air mass is traveling over land and it's coming from high latitudes down. So if it's over land, we say that it's continental, which means it's dry, and it's coming from high latitudes, which means it's cold. So this would be a continental polar air mass. This is coming from low latitude, so it's warm, and it's formed over water. This is the Gulf of Mexico down here. So this is going to be wet. So we call this a maritime tropical air mass, wet and warm. Now, where these two things meet, this is called Tornado Alley. And people travel all over the world to study this area because we've got these cold air masses, and cold dry air masses, and warm wet air masses meeting in this area. Continental polar for air mass 1, maritime tropical for air mass 2. And you can see these are different air masses located around the world based on where they are. Continental tropical air mass, maritime tropical. You can have maritime polar, so it formed over water, but it's really cold because it's up in the high latitudes by the poles. All right, last thing we're going to look at is areas of high pressure and low pressure. Oops, back up, back up, back up, back up, back it up. I'm not going to show you this video, but I would go ahead if you want. I've got this posted on the slideshow. You can click and watch this video. Okay, high pressure. When we are dealing with high pressure, the movement is clockwise. The movement moves outward, and the center cools. Cool air is sinking. So the weather occurs is clear skies, little precipitation, which means little rain or snow, and it's calm. This is like, a nice day. High pressure systems. So air movement is clockwise. It is outward. The air moves out. And in the center, cool air sinks. So we are looking at clockwise would be kind of like this. And as it's moving, it's kind of like it's traveling outwards. So all of this air is going out. And I didn't do a very good job drawing that. Low pressure is going to be the opposite. Low pressure is when the air movement is counterclockwise, but the important thing is air is rising up. And if air rises up, warm air rising, it cools off and forms clouds. Low pressure systems are cloudy days. So here we have nice days. And by nice, I mean like no little clouds. Here, the air movement is counterclockwise. The air moves in. So this would be like your tornado activity. As the air is spinning up, it's basically acting like a vacuum, and all of the air is being pushed in and up. So low pressure systems are associated with tornadoes. So it goes inward like a tornado, and in the center, warm air rises. So what we have here is clouds, precipitation, I'm just going to say precip, and storms. Low pressure system, bad cloudy days, unless you like that. And so what we've got here is we've got these isobars. Isobars show areas of high pressure and low pressure. And so if you are looking anywhere where this line is, it says we have air pressure of 1020. Here we have areas of 1024. Here we have areas of 1028. So this is a high pressure system. It's going from low numbers to high numbers. Here we've got areas of low pressure. The numbers are going lower and lower towards the center. So we know in this area, air is getting pulled in and it's going to be pulled up. These are areas where tornadoes, if you're a weatherman, you're looking for areas like this for tornado activity. Okay, so let's check out what's happening in our United States right now. I want to make this really big. Let's see if I can make this big. And we're going to click on this. And this is what's happening around the United States right now at this moment as far as how air is moving. So you can see the movement of air. There's a lot of convergence right now in Denver. You can see right here, this is Dallas. Notice that all the air is coming from up here and it is rushing down by Dallas and then going in this direction. So you've got all of that cold Arctic air, that continental polar air that is coming right down and is just, keeping that area so cold for those poor people. Here you've got areas, this is the Gulf of Mexico, and you've got nice warm moist air now rising up through this area. That's kind of what's happening. You can see Los Angeles, San Diego. That's what's going on right now. This is all mountainous area. You can kind of see how the mountains make everything. But look at the mountains. The mountains make a barrier right here, so all that cold air just rushes down, just rushes right through here because they're blocked by the Rocky Mountains. Okay, I feel really good about that. I hope that everything went well. I hope that you didn't run out of time. And I'm going to stop the video. So I'll see you later.